Now we are in a position to discuss the third genre of problem which I had listed out in the beginning. So that's about statically indeterminate problems. So to give an idea about what I mean by that, just consider this situation. Okay, suppose there is an annular cylinder which is fixed to the wall on this side. Okay, so this is an annular cylinder, and so I'll just shed it to show that. Okay, and then inside that there is another solid cylinder like that, and you have attached a rigid plate sort of on this side. So this is not flexible. You assume that this is not flexible. Okay, now so let me say that maybe this is of area A2 and E2, and this is of area A1 and E1. Okay, so the materials are different, and obviously the area are also different. And then what you do is you apply a force from this side. Okay, then what happens? Now both of them have to be compressed the same amount because this plate is rigid. Okay, so this is rigid. So once you apply the force, both the annular and the solid cylinder will try to be compressed. Now as soon as they try to get compressed, obviously they will resist this compression. But do you think that the resistance to this compression, will it be same for both? It will not be, right? Because suppose one of them is very weak in resisting, suppose a soft material, then obviously its contribution towards the opposition is smaller than the other one, right? So that's why the amount of sharing of this load, okay, which both of them are having, so that will depend on all these things, the E and the A, everything. So those so if we say that the force which so this is F1 and say this is F2, now this F1 plus F2 will be equal to F. Okay, finally when they are in equilibrium, the resistive force from this and from this, they will have to balance this F. Now this is fine, we can write this, but if we have to tell how much is this and how much is this, if we do not consider the flexible nature of this, that is the displacement, if we don't consider that, then there is no way in which we can actually evaluate them individually. For example, if these are rigid, if you consider them to be rigid cylinders, then there is no way in which we can actually tell that how much is F1 and how much is F2. So that's why we call them statically indeterminate problem, where these two forces cannot be determined individually. Only you can say that together they are equal to F. One more situation where this kind of problem comes is like this. Suppose you have a rod, consider it to be massless, there's no need to make it complex by thinking about the mass. Okay, so our idea is this rod is connected to both these walls or roof, whatever, rigidly. Okay, so these connections are completely fixed, so it cannot slip or move like that. Okay, and then what you are doing is you are applying a force like this at some distance, say A from the top and a distance B from the bottom. Okay, Now what happens? So you think about the reactions now. See, because this F is trying to push it down, obviously this flow will try to push it up. So I'm calling it, say, F from the floor, F from the floor. And because it is trying to pull it from the roof, obviously roof will try to pull it up. So I'm drawing this as F roof. Now obviously the whole system is in equilibrium, so we can simply write that F of roof plus F of the floor must be equal to F. No other forces are acting like gravity, okay? So, but then if we are supposed to find out individual forces FF and FR, that's not possible if you do not consider the flexibility of this material. If it is considered to be a rigid rod, okay, or cylinder, then there is no way in which we can determine individually FR and FF, and that's why this case also is considered to be a statically indeterminate problem. But then if we use the displacement, or if we consider the bodies to be slightly flexible, and then we can get another equation which generally we call a compatibility equation. That means the displacement should be compatible with the geometry and the constraints which the system has, okay. Now so that those things if you consider, then you can write one more equation between them, so that you can actually figure out individually how much are these forces, okay. For example, suppose in this case you can say that suppose the displacement which happens is, say, delta, okay. Now that delta it has to be for both the cylinders. Now suppose for this you write, so suppose that is F2, right? So F2, it is the share of load which this annular cylinder is taking, say, is F2. F2 over A2, it is its stress, and the material property E2, okay, Young's modulus for that. So this is the strain which you get, and the length of the whole thing suppose is L, okay. So this is what the compression which is expected to have happened for this annular cylinder, but that must be equal to the other part also, F1 L over A1 E1, okay. So this is the delta which same for both. Now this is what I was talking about, another equation. So I'll write, say, this is equation number 1 connecting F1 and F2. This is equation number 2 connecting F1 and F2, okay. Then all other things assumed to be known. For example, the external load F is known, A1, A2, E1, E2 are known, length is known, then you can figure out F1 and F2. So that's what I was talking about. If you consider this small flexible nature of the bodies, then you can write another equation, the compatibility equation. And I was talking about, right, compatible to the constraint and the geometry. What is the constraint? The constraint that both of them have to move equal amount, okay, they cannot move differently. So that's the meaning of constraint. And I was talking about the geometry also, right? So geometry means, suppose instead of this inner solid block being of the exact same length, suppose it was of slightly smaller length, then you could have written that, okay, if delta is for the annular one, then delta minus that small alpha distance should be the deformation of this. So that I consider as constraint plus geometry and everything, okay. So the point is, using that you can write another equation relating F1 and F2, then you can solve them individually. So exactly in this case also the same thing happens. If you consider this the free body diagram of the upper part, you know, how will you write the free body diagram of the upper portion? So suppose this is bad drawing, okay. So this suppose is the upper one, and so let's say FR is acting, right? So this side also you should show FR, because you know how to draw the free body diagram by taking a considering a cross section somewhere here, and because this is in equilibrium under the force here, FR and nothing else, so that means at every location the force should be FR. So this is the free body diagram of that. So this portion is in extension. Okay, so it will have a delta, we will say extension, and then if you consider the free body diagram of the lower part, you will have say like this. Okay, and the force is, say, it's coming from this side, FF, and it should come from here, FF. Okay, so this length is, say, B, so this length is B, and this length is A. Okay, now when so now these problems are exactly the same as the configuration of canonical problem. Okay, and then in terms of FF and FR, you can write the deflections. And now the question is, what is the compatibility equation? The compatibility equation is, so here if I say it's delta compressive, then, and suppose you consider delta compressive to be negative and delta extension to be positive, then you can write the equation as delta extension plus delta compression should be equal to 0. This is one way to write if you consider the signs inbuilt into them. Otherwise, another way of thinking is, which is sometimes easier, that whatever is the magnitude of the extension of the other one should be the magnitude of the compression of the bottom one, because there could not be any there cannot be any discontinuity in the displacement, how much ever this point comes. So it happens for both the parts. Okay, so this condition if you apply, so in this case again you will get the same type of equations, right? So how much will be this? So F over, say, area is capital A over E times B is, say, delta C. Similarly here it's FR times AE times A. Now these two are equal. From there you get the relationship of what? FB is equal to FRA. Okay, so FB over FR is A over B. So that means, see this, let me write that from here, FF over FR, sorry, this should be capital FR, is equal to A over B. Fine. Now suppose in this case A is small, B is large, so that means this number is smaller than 1. That means FF is smaller than FR. Okay, so FF is smaller than FR. So what it means geometrically is this side or this segment is slightly softer as compared to this side, and that is why the load sharing capability of this portion is small. So that's why FF, the floor side, is smaller than the roof side. Okay, and as you might be remembering that we had defined, F over delta is EA over L. So it was the stiffness. So we had defined some stiffness of a rod for extension or compression to be like this. So having this to be a constant, EA for constant for both, so only thing is the L. Okay, so that means if the length is more, its stiffness is less. So in a way, softer spring. Okay, you can think like that. Now if it is a softer spring, it will share less load, and the stronger one will take the majority of the load. Okay, so that's what this equation tells, and primarily what I mean is this is another equation along with this which can be solved to get FF and FR individually. Okay, so these types of problems are called the statically indeterminate problems, where you will have to use the equation of compatibility to solve individual forces. Here I can make one more point, saying that because I talked about stiffness, everything that you have taught or learned about combining springs in series, in parallel, all those things you can actually use to solve such problems. Okay, for example, to know about whether two springs are in series or in parallel, what you should think is about two parameters, that whether they are sharing the load and they have a common displacement, either this or sharing the displacement and common is the load. Okay, like so this, when they are sharing the load, so they are in series. I mean not the resistive series, remember when you had these resistances like that and you had a voltage, right? So this is R1 and R2. So what was happening? So they were sharing, say here V1 and here V2, and the current which was going through them was common. So current is, suppose you take the analogy like this, that the current is analogous to displacement and the force is like the load which you apply. In this analogy, so you will say that these springs are in series if this happens. And the other condition that, okay, so this I'll draw in the other way. So okay, now in this case, so whatever voltage is there, so the same voltage is across both R1 and R2, but what they're sharing is the current. So that means the load is common, the load is like the voltage which is common, but what they're sharing is displacement. So that is the shared one, so that is parallel. Okay, so that means in our previous problem or discussion, what we were seeing, so you see here, in this case, look at this 1 and 2. If these are two different systems, what they are sharing, they're sharing the load, the F is coming, the load F is coming and both of them are sharing it. But then what is common? The displacement. Okay, sharing, load is shared and displacement is common. Load is shared, displacement is common. Is it so? Yeah, so load is shared, yeah, so they are in series, you can say. Okay, so you can just add them like the normal way. And if you go here again, in this case, yeah, so the displacement is common again, yeah, and they are sharing the load. So this also is the case of the series. Am I right in that saying? Yeah, just a minute. Sharing the load, common displacement, yeah. So series, parallel, and here their common displacement, sharing the load, yeah. So that's how you can see how the thing. So whether things are in series or parallel. For example, if you take another case like this. So suppose this is okay, a system where you have a wall like that, and from here you have another portion. Okay, you are applying a force from this side, and this inside material is something else. Okay, this is another solid rod. But then you have to see that in this case, if you look at see this annular cylinder, a stepped cylinder, okay, this is annular stepped cylinder. It has got two portions. Now what are the sharing and what is common? Sharing and same, common. Now if you see the force, suppose F1 is being shared by this, okay, suppose F1 comes to this. Now the same F1 is also being felt by this portion, but they're sharing the displacement, okay. This will be deflected by something, this will be deflected by something, which will be equal to the total displacement. It means that displacement is shared, but the here only it's right, displacement is shared and the load is common. So that means they are in parallel. And now if you compare that with this, so they are sharing the load, this and this, if you consider the green one and the yellow one, they are sharing the load, but the displacement is common. So the displacement is common, sharing the load, so they are in series. So now this one is say K1, this is K2, and this is say K3. So you will have something like, so this one is say K3, it is in series with, sorry, this is K3 with something like this, okay. So this one is K1 and K2, so they are in parallel and this is in series, so you can apply the stiffnesses of individual item to get the total deflection. So like that you can also, whatever you have studied about the series and parallel things about resistors, you can apply them to solve problems of springs and rods like this, of statically indeterminate structures. So okay, so that was all about the three genres of problem. One was with constant say area material, but with discrete forces or steps of areas and all those things, then continuous changes of area, material or force, and then in this case it is constrained so that the rigid wise, if you consider the bodies to be rigid, the problem becomes statically indeterminate. So these were the three major types of problems which generally you will come across, and then always when you see any problem, try to categorize them into one of them, and then it will be easier to solve the problems. Okay, see you then in the next segment with another topic. We'll stop here for this segment. Bye bye.